In the pre-Columbian Americas, a sophisticated agricultural system fed millions while building soil fertility, conserving water, and sustaining biodiversity. Today, modern industrial agriculture depletes topsoil, drains aquifers, and relies on petroleum-based inputs to feed the world. The contrast reveals an uncomfortable truth. We may have forgotten more about farming than we've learned. The system in question is the Mesoamerican milpa, along with similar polyculture approaches practiced across the Americas, Africa, and Asia. These weren't primitive techniques awaiting European improvement. They were masterworks of agricultural engineering that modern science is only beginning to understand and appreciate. The traditional milpa system, still practiced in parts of Mexico and Central America, revolves around the three sisters: corn, beans, and squash. But calling it a three-crop system misses the point entirely. A traditional milpa might contain dozens of plant species, each playing specific ecological roles while providing food, medicine, or materials. The genius lies in the relationships. Corn stalks provide structure for climbing beans. Beans fix nitrogen from the atmosphere, fertilizing the corn and enriching the soil for future crops. Squash leaves shade the ground with their broad, prickly foliage, retaining precious moisture and suppressing weeds that would compete for nutrients. Together, they create a microclimate that protects the soil and maximizes productivity per square foot. But the three sisters are just the foundation. Traditional milpa farmers understood succession planting in ways that modern agriculture is only beginning to appreciate. They planted crops with different maturation times, ensuring continuous harvests throughout the growing season. Fast-growing greens would be ready first, followed by beans, then corn, and finally winter squash that could be stored for months. The spatial arrangement was equally sophisticated. Farmers didn't plant in rigid rows, but in strategic clusters and patterns that optimized each plant's access to sunlight, water, and nutrients. Tall plants were positioned to avoid shading shorter ones. Deep-rooted species were interspersed with shallow-rooted ones to use soil resources efficiently across different depths. This three-dimensional thinking about the growing space maximized every cubic foot of soil and air. Indigenous farmers didn't stop there. They interspersed tomatoes, chiles, amaranth, and herbs throughout the field. Some plants attracted beneficial insects, others repelled pests. Many served as backup crops if one of the three sisters failed. The result was a resilient food system that rarely experienced total crop failure. Modern agronomists have measured milpa productivity and found results that challenge conventional wisdom. While industrial monoculture might produce more corn per acre, the milpa produces more total calories and nutrition per acre when all crops are counted. One study in Mexico found that milpa systems yielded up to 20 tons of food per hectare annually, comparable to or exceeding industrial yields, while requiring no synthetic inputs. If the milpa impressed with its ecological sophistication, the Chinampa system of the Aztec Empire was agricultural genius on another level entirely. These artificial islands, built in the shallow lakes of the Valley of Mexico, may have been the most productive agricultural system ever devised. Chinampas were constructed by staking out rectangular plots in the lake, typically about 30 meters long and 2.5 meters wide. Farmers drove wooden stakes into the lakebed to mark boundaries, then wove branches between the stakes to create a frame. They filled these frames with alternating layers of mud, dredged from the lake bottom, decaying vegetation, and rich sediment. Trees, particularly willows called ahuejotes, were planted along the edges where their extensive root systems stabilized the islands and prevented erosion. The construction process itself demonstrated remarkable engineering understanding. Farmers built up the Chinampa layers gradually, allowing each to settle and compact before adding the next. The final surface sat just above water level, creating optimal moisture conditions. Narrow canals separated individual Chinampas, providing both transportation routes and a constant source of water and nutrients. The maintenance cycle was equally ingenious. Farmers periodically dredged nutrient-rich muck from the canal bottoms and spread it on the growing surfaces, renewing fertility without external inputs. They composted crop residues and returned them to the beds. Water hyacinth and other aquatic plants were harvested from the canals and used as mulch and fertilizer. The entire system functioned as a closed-loop ecosystem where nothing was wasted. The productivity was staggering. Historical records and modern reconstructions suggest that chinampas could produce up to 7 harvests per year. They required no fallowing, no crop rotation, and no external fertilizer. The lake system itself provided everything needed for continuous cultivation. Tenochtitlan, the Aztec capital built on Lake Texcoco, housed between 200,000 and 400,000 people at its height, making it one of the world's largest cities in 1500. The chinampa system feeding this metropolis covered approximately 9,000 hectares and produced enough surplus to support a complex civilization complete with full-time artisans, priests, warriors, and administrators. When Spanish conquistadors first saw the chinampas, they called them floating gardens and marveled at their beauty and productivity. Bernal Diaz del Castillo, who accompanied Hernán Cortés, wrote that the gardens were a thing to behold and that the causeways connecting them seemed to stretch endlessly across the water. The erasure of these systems wasn't accidental. It was deliberate, systematic, and driven by a combination of colonial ideology, economic interests, and genuine misunderstanding. Spanish colonizers saw indigenous agriculture as primitive. They believed European-style wheat farming and cattle ranching represented progress and civilization. Colonial administrators imposed new crops, new techniques, and new land tenure systems that disrupted traditional practices. The chinampas suffered particularly swift destruction. Spanish engineers drained Lake Texcoco, partly to prevent flooding and partly to create more land for European-style agriculture. By the 1900s, most of the lake system had vanished. Today, only a small fraction of the original chinampas survive, mainly in the Xochimilco neighborhood of Mexico City, preserved more as tourist attractions than working farms. The milpa persisted longer in rural areas, but faced constant pressure. In the 20th century, the Green Revolution promoted high-yield monoculture varieties and chemical inputs as the path to food security. Government agricultural programs encouraged farmers to abandon traditional polyculture for specialized cash crops. Land reform programs often broke up communal holdings where traditional agriculture thrived, replacing them with individual plots more suited to industrial methods. Economic factors accelerated the decline. Traditional milpa farming is knowledge-intensive and labor-intensive. It requires understanding dozens of plant species, their interactions, and the local environment. This knowledge, passed down through generations, began disappearing as young people migrated to cities. Meanwhile, industrial agriculture offered the promise of higher cash incomes with less manual labor. The disappearance of these systems represents more than nostalgia for a romanticized past. We lost practical solutions to problems that now plague modern agriculture. Modern farming depletes topsoil at alarming rates. The United Nations estimates that at current rates, the world has about 60 years of topsoil left. Industrial agriculture requires heavy tilling, which exposes soil to erosion, kills beneficial microorganisms, and releases stored carbon into the atmosphere. In the United States alone, soil erosion costs an estimated $44 billion annually in lost productivity and water contamination. Iowa, heart of the Corn Belt, has lost approximately half its topsoil since farming began there in the mid-1800s. Traditional systems built soil. The milpa's diversity of plants, some with deep roots and others shallow, created complex underground networks. These root systems acted as soil architects, creating channels that improved water infiltration and aeration while holding soil particles together against erosion. Continuous ground cover prevented the raindrop impact and water runoff that causes erosion. The natural cycle of growth and decay added organic matter continuously. Farmers who practice traditional milpa methods report that their soil quality improves over time rather than degrading, with soil carbon levels increasing by 1 to 2% annually in well-managed systems. The soil food web in traditional systems functioned at a level of complexity that modern agriculture struggles to replicate. Mycorrhizal fungi formed partnerships with plant roots, extending their reach for water and nutrients. Nitrogen-fixing bacteria colonized root nodules, pulling nitrogen from the air and converting it into forms plants could use. Beneficial nematodes, earthworms, and countless other organisms processed organic matter, making nutrients available while improving soil structure. This living soil required no synthetic fertilizers because the biological processes created fertility naturally. Water use presents another stark contrast. Industrial agriculture accounts for approximately 70% of global freshwater withdrawals. In many regions, farmers pump water from aquifers faster than rainfall can replenish them. The Ogallala Aquifer, underlying the American Great Plains, has dropped over 100 feet in some areas, threatening the long-term viability of farming in America's breadbasket. California's Central Valley has experienced land subsidence, the ground actually sinking, because so much water has been pumped from underground. Some areas have dropped more than 28 feet, permanently reducing the aquifer's water-holding capacity. Chinampas required no irrigation beyond what the lake system provided naturally. The raised beds drew moisture from the surrounding water through capillary action, the same phenomenon that pulls water up through a paper towel. The constant water table eliminated drought stress, while the elevated beds prevented waterlogging. Farmers occasionally added lake muck for fertility, but the system was essentially self-maintaining. Modern attempts to recreate chinampas have confirmed their water efficiency. A chinampa uses approximately 1/10 the water per kilogram of food produced compared to conventional agriculture, while producing year-round rather than seasonal harvests. Biodiversity loss represents perhaps the most serious consequence of abandoning traditional systems. Industrial agriculture depends on genetic uniformity. The same corn variety might be planted across millions of acres, creating vulnerability to pests, diseases, and climate variations. The Irish potato famine of the 1840s, which killed over 1 million people, resulted from dependence on a single potato variety susceptible to late blight. Traditional milpa systems maintained incredible genetic diversity. Farmers saved seeds from multiple varieties, selecting for different traits, some for taste, others for drought resistance, early maturity, or specific culinary uses. This genetic library provided resilience against whatever challenges might arise. Estimates suggest that 75% of crop genetic diversity has been lost since 1900, as farmers worldwide abandoned traditional varieties for uniform commercial seeds. Much of that lost diversity existed in systems like the milpa, where hundreds of corn varieties adapted to specific local conditions were maintained through continuous cultivation and selection. In recent decades, scientists and farmers have begun rediscovering what indigenous peoples knew millennia ago: agroecology, permaculture, regenerative agriculture, and similar movements all incorporate principles that traditional systems mastered long before these terms existed. Research institutions are studying traditional practices with modern tools. Studies using stable isotope analysis, soil microbiology, and advanced modeling techniques have revealed the sophisticated nutrient cycling in milpa systems. The complementary root structures of the three sisters, for instance, access nutrients at different soil depths and create channels that improve water infiltration and aeration. Climate change adds urgency to this rediscovery. Traditional systems developed over centuries of farmer observation and experimentation, creating varieties and practices adapted to local conditions. As climate zones shift and weather becomes more variable, The resilience built into diverse polyculture systems becomes increasingly valuable. Some farmers are actively reviving traditional methods. In Mexico's Yucatan Peninsula, the Mayan community of Mani has restored traditional milpa cultivation, integrating it with beekeeping and forest management. Their experience demonstrates that traditional systems can compete economically with industrial agriculture when their full value, including environmental services and nutritional diversity, is properly accounted for. In Mexico City, projects like Yolcan and Tzampa work to restore and expand the remaining chinampas of Xochimilco. These initiatives combine traditional knowledge with modern organic farming techniques, producing high-value vegetables for local markets while preserving an endangered ecosystem. The projects also serve as living laboratories where researchers study the ecological processes that made chinampas so productive. The story of traditional farming systems offers several crucial lessons for addressing modern agricultural challenges. First, productivity shouldn't be measured by single crop yields alone. The milpa might produce less corn per acre than an Iowa cornfield, but it produces more total nutrition per acre while building rather than depleting natural capital. When we account for environmental costs, soil erosion, water depletion, biodiversity loss, fossil fuel inputs, traditional systems often outperform industrial agriculture in true efficiency. Second, knowledge matters as much as technology. The sophisticated understanding of plant interactions, soil ecology, and seasonal patterns embedded in traditional farming represents accumulated wisdom from thousands of years of observation and experimentation. This knowledge, adapted to specific landscapes and climates, can't be easily replaced by generic technological solutions. Third, diversity provides resilience. Whether genetic diversity in crop varieties, species diversity in planting schemes, or diversity in farming systems across a landscape, variety buffers against the unexpected. As climate change brings more frequent extreme weather and new pest pressures, the resilience of diverse systems becomes increasingly important. Fourth, agriculture can regenerate landscapes rather than degrading them. The choice between feeding people and protecting the environment is a false dichotomy created by industrial farming's destructive methods. Traditional systems demonstrate that intensive food production can coexist with healthy ecosystems. Reviving traditional farming systems doesn't mean returning to pre-industrial society or rejecting all modern knowledge. Rather, it means integrating the ecological wisdom of traditional practices with the best of contemporary science and technology. Some hybrid approaches show promise. Researchers in Mexico have developed milpa systems enhanced with precision agriculture tools that help farmers optimize planting times and spatial arrangements while maintaining the fundamental polyculture design. In other regions, traditional terracing techniques combined with modern water harvesting technology create highly productive systems suited to climate change conditions. The challenge is institutional as much as technical. Agricultural research, extension services, and subsidy programs remain oriented toward industrial monoculture. Shifting toward agroecological approaches requires changing not just what farmers do, but how agricultural knowledge is generated, shared, and supported. Market structures matter too. Industrial agriculture benefits from economies of scale, specialized equipment, and commodity crop infrastructure. Traditional polyculture systems need different economic models: shorter supply chains, direct farmer-to-consumer relationships, and proper valuation of environmental services. Some governments are beginning to recognize these realities. Mexico's Sembrando Vida program pays farmers to plant trees alongside crops using milpa principles. Several African nations promote intercropping and agroforestry as climate adaptation strategies. These policies acknowledge that the cheapest, most effective agricultural technologies might be ones we already discovered thousands of years ago. The 3,000-year-old farming systems of the Americas, Africa, and Asia weren't erased because they failed. They were erased because colonialism, industrialization, and economic forces favored uniform, extractive approaches over diverse, regenerative ones. We traded sustainable abundance for productive fragility, then convinced ourselves it represented progress. The good news is that this knowledge isn't entirely lost. Communities still practice traditional agriculture. Seeds preserved in seed banks and farmers' fields retain genetic diversity. The ecological principles underlying traditional systems remain valid regardless of whether we acknowledge them. As industrial agriculture confronts its inherent limitations, depleted soils, drained aquifers, climate instability, and biodiversity collapse, the 3,000-year-old alternative looks less like a relic and more like a blueprint. The question isn't whether these systems worked. The historical and scientific record clearly shows they did. The question is whether we're wise enough to learn from them before it's too late. The milpa and chinampa aren't museum pieces to be preserved behind glass. They're living systems that evolved to solve precisely the problems modern agriculture struggles with. In an era of climate chaos and resource constraints, perhaps the most innovative thing we could do is remember what we once knew and build on it. The future of farming might look remarkably like its past. Only this time, we'll understand why it works so well.